Hi, welcome to another video podcast. Today we'll be looking at the photoelectric effect. This will form the second of the three videos covering the basic quantum theory that you need to know. We'll go back to the beginning and I'll just talk you through the demonstration that we saw at the beginning to kick all this off. We took a negatively charged plate. We noticed that if we shone long wavelength radiation onto the plate, for example red light, no electrons are removed. No, the plate remains charged. However, if we shine blue light onto the plate rapidly becomes discharged. We also, for completeness, try a positively charged plate. It didn't matter what we did, no radiation could remove the charge from the positively charged plate. However, I said before, blue light would and red light wouldn't remove the radiation. First of all, we can explain this fairly easily. It is electrons that are the free charge carriers. They're the ones that are being knocked off the metal surface by the radiation, and you can't remove positive charge by removing electrons. We'd have to add electrons. The radiation itself is neutral, it's not carrying any charge, and that wouldn't be able to discharge the plate. This created a major conundrum for early 20th century physics. The wave model of light at the time was a very good, well-established theory. We knew that blue light had a short wavelength, and we imagined bright blue light with simply the same wavelength, not doing particularly well there, but a much greater amplitude. Red light has a much longer wavelength. Similarly, we can have a large amplitude or we can have a small amplitude which represents the amount of energy the wave is carrying. But there's nothing in classical physics, in wave theory, to say why a dim blue light, small amplitude wave, will discharge our metal plate, but however bright we make the red light, it's unable to discharge the metal plate. There was another problem for the 20th century wave theory of light, explaining the photoelectric effect. We imagine in the wave theory of light that the light arrives uniformly all over the metal surface, just like the board here is illuminated by light. We imagine every part of the board receiving the same amount of energy per unit area per second. We'd have really quite a lot of energy is needed to release an electron from the metal surface. The electron is very localized and it's going to form a very small area in the metal surface. So how is it that as soon as we turn on the light, immediately electrons are released? It doesn't look like the energy is arriving uniformly over the surface. It looks like the energy is concentrated into particular points on the metal. Step forward, Albert Einstein. We now use Einstein's explanation of the photoelectric effect. I'll draw you just a metal plate. And we imagine now that the light that's arriving on the plate is particles. I'm just going to draw one of those particles of light, or photons, or quanta. It's just a little packet of energy. If we just visualise a light giving out the photons, we now need a new model for intensity or brightness. There aren't any waves to have a larger amplitude anymore. So a bright light simply means a light that gives out more photons per second. So a bright blue light gives out many more photons per second compared to a dim blue light. But that doesn't change the nature of any one photon. All the photons are identical. Einstein proposed that the energy of the photon was given by h, Planck's constant, multiplied by f, frequency. And that energy is given to a single electron, as one photon hits one electron within the metal surface, and if the energy of the photon is sufficient, the electron will be removed from the metal surface. The rule being that the energy of the photon must be greater than the work function of the metal for there to be any chance of removing an electron from the metal surface. The work function is the minimum energy needed to remove an electron from the metal surface. Now in general terms, if we are removing electrons from the metal surface, the chances are that there will be some spare energy left over, and that will be in the form of the kinetic energy of the electron. So the original energy of the photon is split between two things. It's split between removing the electron from the metal surface and the kinetic energy of the electron. And that allows us to write an equation, HF equals phi plus EK. The energy of the photon is equal to the work function, the minimum energy required to remove an electron from the metal surface, plus the maximum kinetic energy of the electron that's been removed. We sometimes use the word photoelectron for these electrons. Another term that's useful to note is the term threshold frequency, which we often write F0. That's the frequency of radiation just capable of removing an electron from the metal surface. Now obviously if we're just removing an electron from the metal surface, we're using a very minimum amount of energy, we can say that EK is 0 and simply have HF0, Planck's constant times the threshold frequency, is equal to phi, the work function. Thank you very much.